This next section adds two more types of tests. Both of them are comparison types of tests, comparing something that we don't know, a series we don't know, compared to a series that we do know. And recall there are a couple of series we want to keep in mind. The geometric series, the P series are very common series that we're going to use to compare other series. So the comparison test, the first one is the comparison test. And so we have two series. The B series is the series that we know about, and the A series is the series we don't know about. If the B sub n series is convergent, and the A sub n terms are smaller than the B sub n terms, then the A sub n terms is also convergent. So we're comparing a known convergent to a smaller unknown convergent. The next one is a known divergent, and then the A sub n's are larger than the B sub n's, so then the A sub n's are divergent. So here's an example. This is more complicated than some of the ones we've seen previously. Notice these extra terms down in the denominator. We want to compare this to a known series. So it makes sense to say, you know, if I didn't have to worry about these other terms in the denominator, this would be an easier problem to work with. So let's call our b sub n 5 over 2n squared. So our summation is 5 over 2 times 1 over n squared, or 5 halves times the sum of 1 over n squared. So what can we say about this series? Well, you can say that it is a convergent P series. Since P is 2, it's a convergent P series. So is this B sub n always larger than the A sub n? The answer is yes. Notice we don't have to do anything too fancy. Notice everything is the same except for these terms right here. If we're thinking about fractions, and if we're thinking about adding something to the denominator of a fraction, remember n is 1 or bigger, so this part compared to this part right here with the 0, 4n plus 3 is always going to be bigger than 0. So taking these fractions, we know the fraction with the larger denominator is a smaller number, so we have a convergent, this looks similar to a convergent p-series, and that's it. We're done. We don't have to determine what the limit of this thing is, and for our purposes, we're usually going to skip the estimating the sums and just determine whether or not they are convergent. The next one is one we've seen previously. So we already know how this one should work. This one should be divergent, right? So how can we determine whether or not this is divergent? Well, previously we used the integral test to see that this was divergent. What can we compare the ln of k divided by k with? Well, it is larger than 1 over k. Why is it larger than 1 over k? Why did we pick 1 over k? ln of k, think about the values for k. K is 1, 2, 3, and so on. Now, just a reminder, when we say that this is with positive terms and also one's bigger than the other, really we only care about the large values of k, or the tail, I guess you could say, of this thing. When k is 1, we would actually have a 0 on the left-hand side of this inequality. Um, so this is actually true when k is greater than or equal to 3. But that's big enough because it's greater than or equal to 3. This inequality stays true. So why am I looking at this inequality? What do I know about the sum of 1 over k? Well, we know that's the harmonic series, and if something smaller diverges, then the larger one will also diverge. So what do we know about the harmonic series? Well, harmonic series is also a p equals 1 p series, p series, and that is divergent.